Hi guys, my name is Shay. I'm the CTO of the group called Tactics, which is an advanced security center of Payload. I'm here to present a new project called Divination, but before that, a few words about Tactics. Tactics used to be a privately held boutique company that was bought by Ernst & Young in 2011. Since then, somebody actually funds my researches. I too mangle the English language. And since this presentation is designed for penetration testers, security researchers, techies in general, it's going to contain plenty of technical English, so I apologize in advance for any words that aren't actually part of the English vocabulary. So, I'm here to present a project called Divination. Divination is a new OWASP ZAP extension. It's an open source project that we have been developing for over a year. We've got plenty of support from the guys behind the ZAP, particularly from Simon Bennett. And what these tools aims to do, it aims to enhance the manual penetration testing process, to provide a set of tools that currently testers don't have in any other commercial or open source tool in the market. It implements a new set of information gathering attacks called Divination Attacks, which in general attempts to predict the structure of the server-side memory, predict the structure of server-side processes, and even predict the server-side source code, all using nothing but black box techniques. Now, before I'm going to delve into the details and explain the mechanics of the attacks behind this application, I want to show you what the end result looks like. What do you get out of this process that we're going to discuss in the following hour? So, what you're currently seeing, you won't see it too well because the resolution isn't ideal, but what you're currently seeing is a memory map of the server-side application. It's a memory map of a demo server-side application. What you can see in this map is where the server stores variables that were received in user-originating input. You can see output that is stored in session variables. You can see output that is stored in database variables. You can see how each and every input affects the entire application. So this is also a dynamic map. Just by clicking on a value in this map, on a parameter in a specific page, you can immediately see, as a pen tester, which pages in the entire application are affected by this parameter. You can see whether or not the parameter is reflected in the output. Does it cause an exception? Does it change the content? And if it does, in how much percent? Does it cause time delay? You can see how each and every parameter in the entire application affects not only the page of origin, but the entire application. So there's plenty of additional features that I'm going to present in the following hour, but this product, this solution aims to solve a problem. And the problem I'm discussing is a bit different than the problem that is usually the focus of information security talks. I'm not discussing the consumer, I'm not discussing the developer or his lack of information security awareness. My problem is the tester, or more accurately, the limitations of the tester's decision-making process. Now, in order to properly explain what do I mean by the limitations of the tester's decision-making process, let's go over the manual penetration testing phase, or the penetration testing phase, to see where in this process those testers need to use their judgment or actually make any decisions. So penetration testing is a process that is composed from several phases. Testers need to perform various operations during a penetration test, such as fingerprinting, Google hacking, automated scanning, fuzzing, and so on. Eventually, at the end of this process, the testers will get to the main phase of the penetration test, which is manual testing. This is the actual phase in which we, and as pen testers actually attempt to locate vulnerabilities manually in each and every section of the applications. Now, are there any penetration testers in cloud? Raise your hands if there's any penetration tester here. 1, 2, seriously? Okay. I'll manage. So eventually, when we get to the manual penetration testing phase, there's still plenty of tasks that we need to perform, and plenty of attacks that we need to test in each and every section of the application. How many attacks? Well, it depends. According to OWASP attacks and vulnerabilities, probably the biggest list in the internet, there's at least 64 different types of attacks and at least 165 different vulnerabilities. According to OWASP, there's 34 different types of attacks and 15 weaknesses. If you add up lists such as CWE, Wiki, OWASP testing guide, we'll add more and more and more to the pile. So we tried merging all those lists to see how many attacks does the pen testers really need to perform on each and every entry point in the application. And we got to over 100 different types of web application level attacks. That's 100 different types, different categories, not taking into account different payloads or scenarios, just different categories of attacks that should be performed on each and every entry point. And in most cases, in each and every parameter in the application. Now, obviously, that's a lot of work, and let's do the math. Now, if we're testing a small-sized application, let's say somewhere around 20 pages, and each page in the application has about 3 parameters on average, it means that we have to perform at least 100 tests, again, not taking into account any different payloads or scenarios, authentication, without authentication, just the basics, on 3 parameters in 20 pages. That adds up to 6,000 tests. Now, that's a lot, but if we have a time frame of 1 or 2 weeks, we can pull it off. We can probably manage to test most of these vulnerabilities. However, if we're testing a mid-sized or a larger application, something around 100 URLs or more, and we use the same math, so we'll end up with 30,000 tests. And that's 30,000 tests. That's not something that we can actually perform in 2 weeks. In my opinion, we probably can't perform that in 2 months. So obviously, in real life, penetration testers don't always perform the tests that they want to perform manually. They don't have enough time. Customers don't pay millions of dollars for each small application for penetration tests. So they use a couple of techniques, processes, and tools to help them handle the test coverage. Now, there's plenty of those, but let's go over the most common tools and processes. There's, of course, experience, intuition, and luck. The penetration test is also only as good as the penetration tester. But obviously, I won't discuss luck or intuition in this presentation. There's automated scanners, which enable the tester to test for a large number of attacks on a large number of URLs and parameters. And there's fuzzers that do the same, but don't actually make any decisions for the testers. They collect the responses and leave it for the tester to analyze. And there's information gathering processes that help the tester narrow down and focus on locations that are most likely vulnerable or more likely to be vulnerable. Now, all of these tools are great. They really enhance the penetration testing process. They enable us as testers to do a better job, but they all have certain limitations which prevent even them all from providing a complete solution to the test coverage problem. Let's go over the advantages and disadvantages of this solution to understand where are they limited. Now, let's start with automated scanners or web application scanners in our case. Web application scanners can really enhance the penetration testing process. They perform a wide range of attacks on a wide range of URLs, but eventually, a scanner can only detect a URL or detect a vulnerability if it is familiar with that vulnerability. A scanner that doesn't have an SQL injection plugin cannot detect an SQL injection attack. Furthermore, even if a scanner has a plugin for a specific attack, it doesn't necessarily has a good enough logic to be able to detect a specific instance. So even a scanner that has an SQL injection plugin doesn't necessarily or isn't necessarily able to detect all the instances of SQL injection in an application. Fuzzers, on the other hand, don't make any decisions for the tester. They leave it for the tester to analyze the different responses that they gain. They work like scanners. They execute plenty of payloads against plenty of URLs. However, the tester has to actually analyze the responses to see where are the leads, where are the interesting locations. And sometimes, especially in large applications, there's so much content to analyze. There's so much time that the tester needs to invest just to analyze the content that in most cases, or at least in my experience, he prefers to do the manual penetration testing on his own and without the fuzzer. Again, it depends on the fuzzer and the tester, but that's generally the problem. However, information gathering processes provide a different solution. Unlike automated scanning or fuzzing tools, they don't make any decisions and don't tell the tester which locations are vulnerable. However, they obtain information that might help the tester focus on the locations in the application which might be vulnerable. Now, there's two main types of information gathering processes that I'm going to discuss. There's passive information gathering processes, which are generally non-intrusive processes that attempt to obtain information without using any actual attack. So we're not trying to extract more information, we're trying to obtain information that is just out there. Things such as search engines, Google hacking, obtaining or collecting HTML comments, stuff like that. And there's, of course, active information gathering processes. Things such as fingerprinting or file and directory enumeration, processes that attempt to extract additional information in order to aid the tester. Now, there's a small subcategory under active information gathering called manual active information gathering. And the reason I'm bothering to mention this category is that, in my opinion, it's probably the most powerful tool that the tester has. Now, in order to explain what I mean by manual active information gathering, let's go over a simple test scenario. Let's assume we're testing a specific page to see whether or not it's vulnerable to cross-site scripting. So we might want to send an input to see whether or not it's reflected. So we'll send AAAA and check the response to see whether or not AAA is reflected back. What we're actually doing manually is attempting to obtain more information. We're attempting to obtain information about a specific behavior in the application that might suggest that this location is vulnerable. Now, it's really powerful because the tester, when he uses these techniques, he uses the human mind, which isn't limited by patterns. A human mind or tester, a human tester, can actually detect an attack without being familiar with it. He can detect a suspicious scenario, Google it, ask a friend, and eventually locate the vulnerability, even if he didn't or wasn't familiar with it in the first place. So it's a very powerful tool. However, it's an absurd because, in my opinion, it's the most powerful tool the tester has. It's his mind, but he can only use it on locations that he tests manually. And since he only tests a fragment of the application manually, it means that the most powerful tool that the tester has is only used on a small fragment of the application. And the less efficient tools that the tester has, as efficient as they may be, are used on the rest of the application. So it's a problem. And in our opinion, there's a missing phase in the puzzle that is penetration testing. There's a missing process. And we believe that the solution is related to Mr. Big. Now, initially we tried to force the acronym, the initials on Miyagi, just no matter what we did, it didn't work out. So what Mr. Big stands for is massive recursive behavior information gathering. It means, in plain words, that we attempt to collect all the behaviors that the tester would have attempted to locate manually in an automated manner. If testers attempt to locate time delays and exceptions and content differentiation and reflections of output manually, we can detect that those behaviors for the testers in the entire applications in different and extreme scenarios, collect those behaviors and present them to the tester, and that's the key, in a visual manner that will enable him to make decisions quickly based on this information, instead of analyzing each and every response. How does that contribute to the penetration testing process? Let's provide a simple example. Now, I'm assuming most of the crowd is familiar with SQL injection attack. I think that's a fair assumption. Okay, now, I have a very specific instance of an SQL injection attack in this demo application. Now, usually when we perform an SQL injection attack, we might send an input that contains quote or time delay payloads or whatever to a field in the application, to a specific field in a specific page, to see whether or not that field is affected. Does it cause an exception? Is the response delayed? Now, in this specific page, however, although it does receive the input, it is not affected by the input. Instead, it stores the input in a shared variable, in a session variable. And another page, which uses this session variable, which was stored by the first page, is actually the vulnerable page. Again, it's an indirect attack. The input is sent from one page, but affects another from a shared variable. So, detecting those scenarios, those indirect scenarios, manually is pretty difficult if we have a large application. There's many sequences that we need to test. Page 1 to page 3, page 1 to page 6, page 1 to page 10. There's plenty of sequences. It's probably not likely to be able to cover all of them. Furthermore, as far as I know, and I think I pretty much know all of them, I don't know many automated scanners that are able to detect those indirect scenarios for the vast majority of attacks. For example, I haven't seen any scanner that has a plugin that detects indirect LDAP attack sequences. Haven't seen it. So it means that if those vulnerabilities exist in application, they're still in there. People probably haven't detected them, even though they've pen tested the application over and over and over again. However, a tool such as Diviner, which attempts to execute different complex scenarios and collect the information, can identify this behavior immediately. So we have a feature in Diviner called tasks. We'll get to it later. What this feature does, it organizes the behaviors of the application according to categories that you can see. So this category means exceptions that are caused by session variables that the user has control of. And I can immediately see, before even beginning the penetration test, that there's a suspicious behavior that starts in a page called phase 2 and affects a page called segment. So I can immediately see the potential and see which values are required to trigger the event. I can see all the information before beginning the penetration test. That's probably a powerful tool when you're testing a large-sized application instead of just randomly throwing your output or throwing your payload somewhere in the application. You can see which locations in the application are more likely to be vulnerable to different categories of attacks. You can also see reflections of output and other things. We'll demonstrate it later. So when I first got into the information security field about 9 years ago, my mentor, a nice guy called Dr. Mao, which is actually presenting in the next room, he taught me that the best type of information disclosure that can possibly get in a penetration test is source code disclosure. The best type of information disclosure that a tester can get is source code disclosure because source code disclosure enables testers to see the logic behind the scenes, to see which technologies are in use, to see how the queries are structured. So although we can't provide or can't present the real source code, we can present fragments of the source code, enough to make the process worthwhile. So let's assume a tester attempts to test a specific section of the application, and he's about to send an LDAP injection payload. He can use a feature in Diviner called clairvoyance. Translation from France, clear vision. To see a representation of the server-side source code which is relevant for that specific page based on the behaviors that we gathered on this page. And you can obviously see in this example that this page doesn't use, or we don't know of any LDAP server that is used in this code. We can see clearly that this code uses a database. So the tester might make a wise decision to test for SQL injection instead of LDAP injection and not waste his time. Now, don't get me wrong. I'm not suggesting that testers stop doing tests according to their intuition, luck, or whatever. But I am suggesting that it is wiser to perform tests that we know that the lead exists for first. Meaning to do those things first are more likely to occur. So, A little bit history. The idea itself for the Diviner project and for this presentation was actually born in Texas. I was sitting with a colleague of mine in a bar called the Flying Saucer in Houston, and we were discussing the applications of an attack called connection pool consumption. Now, it's irrelevant for our purposes. I won't discuss the attack too much, but in general, what this attack does, it delays the execution of a single line of code. It delays the execution of a line of code that attempts to obtain a connection from a database connection pool. So during this conversation, it dawned on me that there's a secondary conclusion to this successful attack. If we manage to perform such an attack successfully, sure, this page is vulnerable to connection pool consumption. But if connection pool consumption delays a specific line of code and the attack works, and that's probably the basis of the entire presentation, it also means that this line of code exists. I'll let it sit for a while. Imagine an attack that actually succeeds. It is dependent on certain or specific lines of code. Each attack, each vulnerability is based on code. So a successful attack actually suggests that specific lines of code are running behind the scenes, are running in the backend in a specific page in the application. So after a while, I thought about it and I got to the conclusion that each and every behavior in the application, not simply attacks or vulnerabilities, not simply suspicious behaviors, every behavior in the application has code behind it. And every behavior that we can detect can actually be converted or represented as source code. So a feature in the application that redirects the user to another page is a redirection line of code. There's a specific line of code behind this behavior that redirects the user, and I can represent it as source code. So obviously, in order to provide quality content, something that can actually present a real picture, something that is useful to the tester, we have to collect a bunch of behaviors from the entire application and from many, many different scenarios. So in order to succeed at this task, in order to fulfill our goal, we used OWASP ZAP, or more specifically, the history tracking feature of OWASP ZAP. We use OWASP ZAP request history. And what we do in order to generate those behaviors in the entire application is to re-execute each and every request in ZAP's history in different sequences and in different scenarios. So let's do a dry run, just to understand. We'll send a random value to the first parameter of the first request in the history and see how it affects the first request, the first page. We'll send another random value to the first page in the first request in the history and see how it affects the second page. We'll send another third random value to the first parameter of the first page and test how it affects the third page, and so on and so on and so on. We'll try all those sequences that testers don't have time to test manually, and in most cases, automated scanners don't do. Eventually, after doing all those processes, we'll do them again with authentication, without authentication. With authentication between the page in which the input is set and between the page in which the input is tested. We'll do it again with anti-CSRF tokens, without anti-CSRF tokens, and in different and varied conditions. There's plenty of conditions that you do it in. It's a process that takes about 20 minutes for 40 pages. It's long, but the result is pretty good, actually. We get a huge list of behaviors that might apply to one or more pages. We can actually see which parameters affect which pages and how. And we can convert these behaviors into different representations. Now currently we have a specific table in Diviner that defines lines of code or potential lines of code for each and every behavior that we know how to fingerprint. And each line of code can be called from different groups of line of code. For example, a behavior in which the server replaces the session identifier might be caused from a line of code that sets a header, a set header line of code, or from a line of code that invalidates the session and replaces the session identifier, or an invalidate line of code. So in order to verify which line of code is the more appropriate line of code, which line of code should we actually present to the tester, we do a verification process. We take each behaviors and perform verifications on it to see which line of code is more probable to occur. So each behavior, each line of code for each behavior has a default probability. And we perform verifications that either increase or decrease the probability for each behavior. So let's take the example we used earlier. If we have a behavior that replaces the session, I might see, or I might test whether or not the session, the previous session, is actually still alive. If the previous session identifier is still alive, then the probability for the set header lines of code raises. If it's not, then the probability for the invalidate line of code raises. Eventually, at the end of the process, I'll present to the tester which lines of code are probably behind the scenes, the lines of code with the highest probability, and I also present in the left side how sure I am that each line of code actually exists behind the scenes. So that's one form of representation. We're currently able to identify 23 different groups of code, not necessarily lines, groups of code with different varieties. We're also able to identify partly identify the structure of queries. We're able to know whether or not it's an insert, update, or a select query. In the future, we'll be able to know more. We're able to identify specific fields in the database, specific tables, which are shared by several pages. We're able to see session variables which are used or affected by the same pages. We're able to obtain plenty of information, and since we're able to obtain so much information about where the server actually stores variables and input, we're able to present the memory structure of the application. We're able to present to the tester how each parameter affects the application and where the application stores the values received from this parameter. In addition, we're able to present to a tester that currently tests a page exactly how the parameter that he's testing affects the entire application. So if a tester is currently sending an SQL injection payload to a parameter, you can see that the parameter affects a specific page, and the divination process hasn't really detected any other pages that are affected by this value. Okay? So, Divination is currently integrated with a couple of additional open source projects. It's integrated with a project called Payload Manager that adds a couple of additional unique features, again, to enhance the manual penetration testing process. And it's probably the best time for me to stop discussing the mechanics and start demonstrating what the tool can actually do. So, as I mentioned earlier, Diviner is an open source ZAP extension. In order to get to the project page, you have to write Diviner and Google code in a Google search query. If you write Diviner, you'll end up with a weird TV series, which is really, honestly, isn't worth your time. So write Google code alongside Diviner. It has an installer. It's installed as an extension. It's available within OWASP ZAP proxy in the tools menu. There's a launch Diviner feature here. Now, Diviner supports plenty of sequences and extreme scenarios. It supports authentication, CSRF token, .NET, Java, PHP, and a wide variety of technologies. It's currently able to present source code in JSP, but in the future we'll be able to convert this pseudocode into ASP.NET, PHP, or whichever language the developer or the tester will want to see. It has several interesting features, most namely the task list. After an analysis process, Diviner presents all the suspicious behaviors, some of them customly defined by the tester, in a list based on category. And the tester can actually get to a specific behavior, see which page is the input page, which page the input actually affects, and get all the information that it needs to reconstruct the scenario in a feature called Advisor, a feature that contains all the information actually necessary to reconstruct a scenario. Furthermore, in addition to presenting the memory map, Diviner converts the behavior obtained on each and every page into a source code representation so that pen testers, instead of just wasting their time, will see which attacks are most likely to work on a specific page or parameter before testing that page. Now, this is a very problematic representation currently because the screen is really small. So if we have plenty of pages and you want to see only the relevant pages, we have a feature that actually presents all the pages that a specific page affects in a singular representation or in a singular window. Now, the effect of each parameter is translated into an icon, also into text, and I can see immediately that this parameter is reflected in the output, and the output is stored in a session variable, or that the output is stored in a database variable, or that a specific page has an exception due to a specific value that was sent. In addition to all those divination features that attempt to predict the structure of the server, Diviner, as I mentioned earlier, is integrated with another project that is aimed to solve a different problem. And that project is Payload Manager. Payload Manager is a feature that's designed to handle a different problem. And the problem is another limitation of the manual penetration testing process, or more accurately, of the human tester. And that's memory. Testers don't always remember the payloads they need to remember for each and every attack category. If you remember earlier, I presented a huge list of attack categories. We got to over 100 different attacks. Now, most of my pen testers don't remember the payloads required to perform EL injection. Some of them don't necessarily remember the payloads required to perform LDAP injection. So what we did, we gathered all those payloads into a feature that is integrated with ZAP's recent feature. So the tester can actually select the attack that you want to perform on a specific parameter, select the payload. If he managed to gather information on a specific platform, he can even filter the payloads that are more relevant. So if he's testing the system, and the pen tester has found out that it's Linux, it can filter the payloads that are more relevant for Linux or for Windows. Okay? Now, after selecting a payload, he can perform various evasion techniques on this payload, and immediately afterwards asks Payload Manager to transfer the payload to a recent feature of OWASP ZAP proxy. For those of you who are not familiar with ZAP's proxy, it's just like burp repeater, or this specific feature is like burp's repeater feature. And we can actually test manually using this Payload Manager with payloads that we customize for ourselves without having to remember the different payloads that are used. So that's another feature. So, as I mentioned earlier, we have been developing this project for over a year now. It's still in beta phases, but it's stable. It can already find a couple of extreme scenarios and scenarios that we haven't managed to locate using other tools or techniques. The Payload Manager feature is actually in alpha, but it's out there. You can already customize your payload. In case you read an article and you find a specific payload you like, you don't have to remember it anymore. You can write it down. You can then reuse it in your penetration testing process. We have additional plans to develop Diviner. Specifically, we are currently cooperating with 2 open source web application scanner projects. We're going to export the leads that Diviner found in an XML database to those scanners, and they therefore will be able to detect all those indirect scenarios where input is sent to one page but affects another without having to do all the sequences themselves. That's it. That's something? That's pretty much it. Are there any questions? Whoa, won't do information, huh? It's integrated into OWASP ZAP proxy, which is a penetration testing proxy that the browser can connect to. Okay? It works, it analyzes the requests that are found in ZAP system.
So it depends on the
Precisely. The pen testers, in order to properly use this tool, has to manually crawl different pages of the application and then activate the analyze feature. Other questions? Okay.
Is there any way to tell it to exclude certain possibilities?
Of course. Of course. Let's go over the test wizard. I haven't shown it. I admit I was lazy. Now it's time to pay. So you can actually select the domain, the plugins or the test you want to perform, the analysis types you want to do. You can customize the payloads that Diviner sends. It sends generally two payloads. A random valid payload. Payload uses the same character set as the type of field. And an invalid payload. Payload that contains values that are designed to cause an exception or an abnormal behavior. And you can customize those values. Afterwards, you can select which scenarios you want to perform, with login, without login, with the history of the pages that came before the page, without it, and so on. And eventually, you are able to select the URLs that you want to test. So that's the safety feature we will discuss, we will mention. You can actually exclude pages that delete something, or the logger pages, or any pages that might be a risk in this test. It's not as intrusive as a scanner. It's a lot less intrusive than a scanner. It sends a lot less requests than a scanner. It sends, in general, 2 requests per parameter per sequence. Don't know if it means anything, but let's hope it does. We support additional features as well. We support login, defining a login sequence, defining a page or a specific entry point in the application that generates a new session identifier. The logger page, we support defining anti-CSRF tokens and even .NET specific fields which would be replayed over and over and over in each request. We did our best to support as many technologies as possible. Obviously, we don't support everything yet, but it's pretty useful as it is, and it will be developed and maintained by us. Any other questions? Yes?
So when you're trying to figure out what are the pages that get affected by the page you are injecting stuff into, for the worst case scenario, you would go and if every page has inputs, for worst case scenario, you would go inject in every page and look at how it reflects or not in all other pages?
No, actually we'll do the process all over again in order to make sure that session variables or database values aren't overridden. So we'll test to see whether a value affects a specific page, throw the session or create a new session identifier, use this new session identifier and re-perform the process and test the second page. Re-perform the process and test the third page and so on. We'll do it over and over and over again. Yes, I know it's costly. We pay a certain price in performance, but the results are much more accurate that way.
My question is more like, I wanted to figure out what's the complexity. So if you, let's say, have 100 pages and each of those 100 pages has inputs, then you would inject inputs in page 1, and then you go and look if it reflects in page 2, 3, and all the way to 100.
Yes,
then it becomes 100 times 100.
Take the worst scenario you can possibly think. That's it.
Okay.
Seriously, that's what we do. And we don't only do it for reflections. We do it for a different range of categories. We do it for content differentiation. We're taking the content that was in the original ZAP history, the response content. We remove different values that might change from it, such as CSRF tokens or timestamps, and then we perform comparisons to see which characters change. We perform exceptions verifications. We perform time delay tests. We do different tests, but all of those tests are performed in a single instance. So I'll send a parameter, test the effect of this parameter, this value, on a specific page, and in the same test whether or not it's reflected in the output, whether or not there's an exception, whether or not there's a content differentiation, and whether or not there's time delay. But it still is a complex process that it requires a lot of iteration. There's plenty of ideas, and I don't know if you have your specific idea in our roadmap, but we're opening a wiki in a couple of weeks in which we want to get feedback from the community. We're going to present a wiki that actually shows the translation that we currently do to behaviors into lines of code or memory structures and stuff like that. And we're going to get feature requests from the community to see what else is missing in this product to make it more efficient. Okay, guys, my time's up. Hope you enjoyed and enjoy the